So in this video, I will be discussing the differences between static and automatic variables. And let's begin with few examples. So first, let's move on with static variable. So a static variable is initialized only once, and they retain their value during multiple calls or invocation. So suppose if we have a static variable declared inside a function as a formal argument. So if using another test bench, we call that function again and again, it will retain its previous value during its previous call. So allow me to demonstrate this with the help of an example. So I will write a function which will have a return type of int, and I will name this function increment. So the aim of this function is very simple. During each call, there will be a counter inside a function and it will get incremented. So this counter basically says that how many times that this function has been called. And before moving to that, I just want to remind you that by default, every variable declared inside a function, a task, or a module are static in nature. So if I don't use a keyword like automatic and I just write like int I, so this variable is static. So let us begin with this function. I will declare a counter count. I will rather use bit. So during each call, the counter will increment by 1. And it will return the value of count. So let me write a very simple test module. So inside this, I will just go ahead and display the value of count. This will be my first call. Call the function inside the display system task. I will do this again for 2 more times. I will name this call number 2 and this one is call number 3. First, let's check for any compilation error. Okay, it doesn't have any error. So let's emulate the code. So as you can see right here that we are getting 3 values And what is happening right here that inside each display system task, I'm calling the increment function, and increment function is returning the value count. So for the first time, by default, the value of count is 0 because it is of bit type. So during the first call, the count gets incremented and it returns the value of the count right here inside this display system task. Similarly, in the following calls, the same thing happens, but the count retains its previous value during its previous invocation. And it is because of the fact that by default, every variables inside a function or a task or a module are static by default until unless it is explicitly mentioned. So for that reason, we are getting the value of count equals to 1 right here. And after the second call, the count gets incremented and we get the value of count equals to 2. Similarly, in the third call, we get the value of count equals to 3. So do take a note that a static initialization is not synthesizable. So even if we mention something like this and run it, okay. So such kind of initialization are not synthesizable. So let's move on with other example, a very simple one in which you want to pass data through a packet, and there should be a function that will be doing all this stuff of passing a data to a packet. And during each invocation, the function should return a unique ID for each invocation. And for that, the static variable becomes very useful. So let's begin. I will declare this module test. First, I will define a struct data type variable. And the member of this struct will be ID of type int, 8-bit variable data, and that's it. And I name this data type to be packet underscore t, which stands for type. So I will go ahead and write a function. The return type of this function will be the same of that of struct, because it will be returning a struct. I will name this function create packet, and the formal argument is just one, that is our 8-bit data. So first I will declare a variable for packet ID, and I will initialize it to 0. Then I will write the struct and I will name it PKT. And now I will assign the values to the member of this struct. So I initialized it as PKT. So the first member is ID, and I will initialize the ID, the packet ID of the function right here. So the packet ID is a static variable and it starts with 0. But for that, I also need one thing. I want that packet ID to be incremented during each invocation. So we'll write packet ID plus plus. So during each invocation, packet ID will get incremented by 1. After that, I will assign the data, which is a formal argument for this function, to the member of this struct. And finally, I will return the struct. So let's call this function for multiple times inside an initial block. So I will declare 3 structs of type packet underscore t, and I will name them pkt1, pkt2, and pkt3. So for pkt1, I will call the function create packet, and let's assign some value. So for this, I am assigning it to a value in hexadecimal. Right. For packet 2, I'm calling that function again. Okay, for this, let's assign and for this, let's assign great. So after this, we want to display the value of each packet. Let's do that. So first I will display the ID. Let's display the ID in decimal and data in text. So the first member is ID, And the second member is data. I don't know what the hell happened. Anyways, okay. So the second display system task will be for our packet 2. And the third one will be for the packet number 3. So first, let's compile the code to check for any compilation error. We'll quit the simulation. Okay, there are some errors. Let's see. Okay, so I made a mistake here. Oh, wait a second. Got it. Compile it again. Okay, we have one more error. Got it. So for this, select the bit type of 32-bit. Now should work. Yeah, that's fine. So let's simulate the code and check for the result. So as you can see right here that so during each call the function will return the struct of type packet underscore t, and we are just passing the value of data as an argument, and during each invocation there is a static variable packet id, and it will get incremented. So by using that for each invocation we get a Unix id, as you can see right here. So for the first invocation we get the id equals to 1, and for the second invocation we get id equals to 2, and for the third invocation we get id equals to 3. So since it's a static variable, by default it retains its previous value. So for such scenario it becomes very useful. So let's move on with another example to understand the differences between static variable and automatic variable in a better way. So for this example, I will write a function which will count the number of ones inside a binary value. So let's begin. So the return type will be int and it will count the number of ones. So I'm naming it count ones and the argument will be, let's give an 8-bit data. So I will declare a static variable, and by default all the variables declared inside a function will be static and it will be of 8-bit and I will name it count. So I will iterate through the data which will be passed as an argument using for each. So if that particular bit through which we are iterating is high, the count gets incremented. It is this simple. And after doing that for each element, it will return the value of count. So first, let's check for any compilation error. It's fine. So let's write a very simple module test. So first, I will initialize the data that I will pass to this function. Let's name this D and let's pass 8-bit value of, let's say, 1 1 0 0 0 1 0. So this data has 3 ones. So I mean we can see right here that we are expecting the return to be of value 3. So let's find out if it works or not. So I will also declare another variable. Let's name it cnt and it will get the return value from this function. So first I will write an initial block. So this initial block will continuously monitor any changes made to cnt and it will display the value of that on the console. Now I will write another initial block. So inside this initial begin, I will call the function. So I will assign the return value of the function to cnt. Let's pass the t variable and let's run the code. So as you can observe on the console that it is returning the correct value. So the value we passed has 3 ones and it is returning 3. So for this particular case, the static variable is working perfectly. But what happens if we call it for one more time? Let's find out. So in the next time slot, let's give another call. And this time, let's pass the value. For this time, let's give an 8-bit value, which has all the ones. So it should be 8. So which with this call, we are expecting the value of CNT to be 8. But let's find out what happens. So as you can observe on the console that we are getting a value of 11, not 8. So what is happening right here? So with our first call, we get the value of 3, which is perfect. But as I have already mentioned that the static variable retains its value during multiple invocations. So it does count all the ones inside this data, which are 8 ones. But what it did is that it retains its previous value of 3 and it adds the value of 8 to that 3. So for that particular reason, we are getting 11. So for such kind of scenarios, automatic keyword plays an important role because automatic variables initialize during each call during multiple invocations and they are dynamically allocated to different memory locations. So that's why automatic variable here will work. So it's very simple. Just have to add automatic keyword And let's run the code one more time. So as you can see right here that we are getting the correct value for each function call. So for our first case, there were three number of ones and we are getting three. And for our second case, we have eight ones and we are getting eight here. So it is because during each calls, we are getting a separate initialization of the count variable right here. And it is because it is declared to be automatic. So in such cases, automatic plays a very important role. And we could have done this just by writing automatic here. So this makes all the variables inside this function to be automatic. And also remember the automatic initialization or invocation is synthesizable. So that were the differences between an automatic and a static variable. I hope you find this video useful. Thank you so much.